1.2 Mathematical Models. Okay, here we're going to review our basic functions that we learned in pre-calculus and trigonometry, but we're going to do so in the context of mathematical modeling, which is just taking a real-world situation and applying an equation to it to help us make predictions about future events. So here's our process for that. And again, this is just a model of real-world behavior. It won't reflect exactly what's going to happen, but we can use the different models to make reasonable predictions. So the first type of modeling that we can do is linear modeling. We want to do this whenever we are increasing at a constant rate. What defines a linear function is that the slope is constant. So this y equals mx plus b is our slope-intercept form of a line. If we remember, m is the slope and the point 0b is our y-intercept. Another form of a line that we have from college algebra is our point slope form of the line. That's the y minus y1 equals slope times x minus x1 form. M is the slope, x1, y1 is any point we pass through on the line. So as I just mentioned, the key defining feature of a linear model is that the slope is increasing at a constant rate. Notice that these are all going up by the same increment, so are these. So my y value is increasing at the same rate as is what defines it to be a constant slope, okay? Now, a linear function is a type of polynomial. A polynomial is any function of this form right here. The a's are the coefficients, and the n, the highest power that appears, is referred to as the degree of the polynomial. The leading coefficient in conjunction with the degree of the polynomial tells us quite a bit about the shape of the graph, and we'll review that coming up here. So a polynomial of degree 1 is linear, a degree 2 is a quadratic, degree 3 is a cubic, and so on. Our quadratics are parabolas, and so the graph of a parabola with the coefficient being positive opens up, and the graph of a parabola with the coefficient being negative opens down. Okay, so, and we can generalize that every even function is going to look somewhat like a parabola, but as we're going to see coming up, it's a little steeper down in here as the degree gets larger. But as long as the coefficient is positive, this happens. Both arms go up. And as long as the coefficient is negative, both arms go down. A cubic is a degree 3 polynomial, and one arm goes each way on a cubic. So my right arm goes up and the left arm goes down whenever the coefficient is positive. It would be the opposite if the coefficient is negative. My left arm would go up and the right arm would go down if it were a negative coefficient in front. So as I mentioned, this is a degree 4 polynomial. Both arms go up because of a positive leading coefficient, just like the x squared. And this is an odd degree, positive coefficient, right arm goes up, left arm goes down, just like the x cubed. So my power functions are anything of the form x to a constant. And we've looked at some of these, like a parabola already. You should be familiar with these graphs. Y equals x, x squared, x cubed, x to the fourth, x to the fifth. All of these you should know. Now notice that all of the even ones, like x squared and x to the fourth, look kind of like parabolas, but as the degree gets bigger, this becomes flatter in here. And the same relationship with the odd degrees, x cubed and x to the fifth, have the same basic shape, but as the degree gets bigger, we get flatter in here. So my general shape of x to the n depends on the degree n being even or odd. Even, it's going to look kind of like x squared. Odd, it's going to look kind of like x cubed. All right, so this is some examples of showing even, right? This is x to the fourth, x squared, x to the sixth, and odd, x cubed, x to the fifth, and so on. All right, my root function is x to the 1 over n, or x to the square root of the nth root of x. If we remember from college algebra, two things I want to point out to you here. X to the negative 1, remember, is 1 over x. We're going to see that again coming up. And the expression x to the n over m is the same as the nth root of x to the nth power. Okay, so those are basic exponent rules that you should be familiar with. We're using that right here, right? X to the 1 over n is the nth root. It looks kind of like a square root function. Cubed root function looks like this. And a reciprocal function, that's that x to the negative 1 that I just said right there. Okay. So let's go back just a minute. You should be familiar with all of these graphs from college algebra. You should know what all of these basic shape looks like, the domain and the range that goes with each one of them. Again, square root and the cubed root and the 1 over x and 1 over x squared are all included in that. Okay. Our next grouping is rational functions. A rational function is any polynomial over a polynomial. The most basic one is 1 over x. It looks like this. We just saw that. Again, know the domain, the range, the basic shape. Remember that our rational functions have vertical asymptotes, lines that we cannot cross, and horizontal asymptotes are frequently seen as well. The horizontal asymptotes we can cross, they just show us what happens on the ends of the graph. Find the vertical asymptotes by setting the denominator equal to 0, and we will be reviewing how to find the horizontal asymptotes in class. Algebraic functions are any combinations that we've talked about, excuse me, where we're adding, subtracting, multiplying, or dividing any of the functions that we've discussed. All right, now we spent a whole semester studying our trigonometric functions. You do need to know these. So make sure that you are aware of what the sine, the cosine, the tangent all are meaning, what they do, what their basic graphs look like. This is the graph of the sine. Its domain is all real numbers, range -1 to 1, including the endpoints. It has symmetry about the origin. You should know all of these basic properties for the sine, the cosine, and the tangent, as well as how to evaluate these functions on the unit circle. I also expect that you know all of your fundamental identities, the 11 fundamental identities from trigonometry, as well as the double angle for the sine and the cosine. All right, so this is our sine graph. Cosine graph is right below it, looks just the same, except it's shifted. And we can now see symmetry about the y-axis instead of about the origin as we have on the graph of the sine. Domain and range discussed here, and so we know that cosine and sine both go between -1 and +1. Sine and cosine are both 2 pi periodic, so if we add or subtract 2 pi, we get back to the exact same value that we started with. And then the tangent graph, you should again be familiar with this. This one has vertical asymptotes. That's because cosine is in the denominator, so anywhere where the cosine is 0, we would have a vertical asymptote on the graph. The range is all real numbers. Tangent is pi periodic, not 2 pi periodic like sine and cosine. Our exponential functions, this is an exponential growth function because we're getting bigger going that way, right? And as we read from left to right, we're going down on this one. This is an exponential decay function. We have an exponential growth whenever our exponent here, or whenever the base of our exponent is bigger than 1. We have a decay whenever it's between 0 and 1, or if the exponent is negative, and those are equivalent. Our domain is all real numbers. Range is bigger than 0. Logarithm functions. The basic logarithm function has this sort of shape to it. The domain is 0 to infinity. Range is all real numbers. 0 is a vertical asymptote on this graph. So you do need to know all of those basic shapes in order to do well in Calc 1.